Okay, welcome to one of the latest talks of the day. We have survived. So, winning the battle on multiplayer platforms with Everguild. Who am I? I'm Cesar Rios. I'm a game director at Everguild. And what's Everguild? Everguild is a multi-platform developer that it's based on Madrid, but we work 100% remotely. And we are doing, since the very beginning, car collectible games. We started doing Dragonlords, which was good enough to get the IP of Horus Heresy Legions. I suppose we have here the Warhammer fans that were in the keynote this morning. I hope so. So, and after Horus Heresy Legions, we went to do the big bad boy, which is Warhammer 40K, 4,000, and 40,000. And the Dragonlords and Horus Heresy Legions were 2D games completely. All the logic was 2D. Everything was 2D. The scenario tried to mimic a 3D battlefield, but everything in 2D. And for the next game, that doesn't have any sense. And we keep pushing forward to make it better. So we decided to change all the logic to make it 3D. So this is Warforged, in case that you don't know it.
From the eye of terror, we shall bring no mercy. So much to punch, so little time.
My life has been spent preparing for this.
Run, or accept your fate.
In time, I will rule every star. We will conquer this galaxy. This is gonna be a bumpy ride. Form up and advance.
Let the dance of death begin.
Battles like this are what I was made for.
Do we have any Warforged player here? Yeah, some. Nice. So everything that you see here is 60 frames per second in all devices. That's the goal that we aim. If you want to download the game, you can do it there. So what are the challenges that you face when you develop in multiplayer platforms? You always have to consider the input, how the players are going to interact with your game. The UI, completely different aspect ratios, completely different resolutions, so it's always a headache. Performance versus quality, you always want to have the better quality possible at the highest frame rate, saving battery. So this is what we are going to focus on this talk, and the things that we have done to reach that quality level. And also, you have quite a lot of device segmentation, and there are a lot of devices with different GPUs, but also different drivers. So you end up in a situation where everything seems to work, except in one device that has an issue, and you have to fix it. So these are the things that we're going to be talking about how to choose the render pipeline, how we create the scenarios, which are so cool, some technique that we have been using for improving the animations, and how we use shader graph or normal shading coding. So, well, most of you already know, we have the 3 options in here. The legacy one, HDRP, higher quality, but if you are targeting mobile, it's not your options. URP is great, and now with Unity 6 that we have seen in the keynote, it looks like it's going to be even better. So if you target in mobile, your unique option is URP. And also, it's quite important to save development time. Try to have one code base or the same code base for the whole platforms. You save a lot of times in bugs, so in QA and everything. And you can really do that if you plan ahead in how you are going to do the game UX and game UI and everything since the very beginning. You can just go and use the find symbol for the parts that are specific for each of the platforms, like the in-app purchases or the login with the Steam, the login with Game Center. So doing that way, you can safely develop without having to test in all the platforms continuously all the builds that you release. So how we achieve this quality level? No? First, we start with the goal, what we want to get to. And the first one is it should look amazing, preserving what the concept artist had in his head when he started doing that. It should perform perfectly on all devices that we target, which is all OpenGL 3 devices. And it should be cost effective, no? So we can produce. We are not a very big team, so we have to be able to do it in-house. The things that we do to achieve this are the camera projection mapping that we are going to explain because it's like the cool technique here, and then the other ingredients that we put in place to make it look good. Well, normally when you start modeling a scenario, you have the normal steps of one guy who is the concept artist does the concept, then you pass it to another department, maybe other guy who does the 3D modeling, maybe another guy uses the UV mapping, another guy the texturing. And during this process, some details get lost in the middle, or if you don't want to lose that details, it takes quite a lot of effort. So we try to mimic a technique that is most used on cinema, which is rendering the scenario from the camera perspective. That means projecting the textures and everything, doing very simple geometry, and we just bake the texture into that simple geometry. That has the advantage that it's going to look exactly the same as the concept, and the disadvantage that you cannot move freely in the scenario. You have quite limited camera movement, but in a game like ours, which is a card game, we can get these movements whenever the game requires, but you don't have to travel through the scenario doing crazy things, or the player is not in control of the camera, so we can afford to use this technique. These are the several steps that gets in the process, and we are going to be seeing one after another. No? So how everything starts. This starts in Unity, where we put a placeholder scenario with just basic primitives, and we put the cards in place, and we set the camera with the correct field of view and all the correct parameters. Once that we have that ready, we export this to Blender, and we export this as a screenshot to be painted. In this case, we use Photoshop for that. So we pass that to the concept artist, and the concept artist just goes and draws on top of that, without without the freedom that he wants. He does everything in there. The only things that he has to consider is draw whatever is behind some of the objects. No? So in here, instead of just stop drawing in here, he has to go and draw behind each of the objects. After he finishes this, he exports the different layers in different images. So we have the floor, the sandbox, and everything, and we have different textures in place. Then, on Blender, we import the model that we exported from Unity, and in there, you get exactly the same camera parameters and everything, so you have a one-to-one representation of what you have in Unity. And in here, you put also the textures that we have imported from Photoshop and configure each of the materials and each of the objects with one modifier, which is the UV project ones. So whatever the camera is seeing, it projects the texture to the object that it's in the scene. And what's the final result? So this is the concept. And if we put it, this is real time. And that's the proof. So if you didn't notice the change, that's because we did a good job. So you see we maintain one-to-one the same look and feel that the concept artist has envisioned. So let's check this out. So in Blender, we have here the scenario, and this is the camera that we have just exported. We exported from Unity directly. If we start moving around, you start seeing all the tricks. No? Everything gets projected from the camera perspective. If we check the geometry of everything, you will notice that it's very, very, very simple. And we have things like here, like a plane just for the lighting, that then we can animate and do like a fire moving and things like that. No? And if everything gets projected from the camera perspective, we can check, for example, with this tank. If we start moving around it, you will notice that the texture just happens in that moment because it's being projected from the camera. So this also helps to model the things in the correct spot. So you just throw the materials in there, put the projection mapping in here, put in the camera that is going to be used for projection, and then you start modeling. And then you just, with simple place and everything, you start doing that. And now, once we finish this, we import this as an FBX into Unity. And in Unity, we add the particle effects and everything. So we get that concept art, and we bring it to life. OK. Back to the presentation now. What else do we do? For increasing the fidelity, having reflection in the floor for different scenarios, like having paddles, for example, or other type of materials in the floor, is quite important. And in this case, we are using planar reflection. We are lucky here that our game can do that, which is a cheap way of doing reflections. You don't have to go to screen space reflection or anything like that. You can just do this. So in this case, using making camera rendering, we get the camera, we do the projections, inverted. Well, it's the typical way of doing planar reflection. But we also doing depth fading, and then we blur the reflections. And based on the device, we can tweak the quality. So we blur it more, less, or we just avoid blurring at all because it's always an expensive operation. So in this case, we get the color of the camera, then the depth. We mix it together into one texture, and then we do all the blurring stuff. And after having this cool technique and everything, we add on top the post-processing. The post-processing is that the holy grail of post-processing is the bloom HDR and color correction. With that, in this case, this game doesn't have real-time lighting in anything, so there is no need of linear. With gamma space is good enough, so you don't need tone mapping. So just with that, you can do quite a lot of things. And we use the color correction to give more impact to different cards in the game. You can do some actions that change the overall look and feel of the game. So for example, in here, this is just a test of what things you can do just by changing the color correction, going crazy with the blending. So you can get quite a lot of variation just with the color correction. And in this case, what we are using is a texture for sampling that. No? So you get a texture, you put it into Photoshop, you do all the tweaks, and then you import that texture back to Unity. So it's one of the cheapest methods of getting that thing. And then also there are like some additional spells in the game that change the overall look of the match for the duration of the match. And for doing that, we are not using any real-time effects, as I have said. any real-time lightning. So what we do is all the shaders are reading some global parameters that we can tweak, and we can add directly fog in the scenario. We can tint all the things, so we can all the materials in the scenario, so we can turn a scenario which is in day at night, or put it in a sandstorm, or things like that. And we control everything with a scriptable object where the artist can go there, tweak all the parameters, and just switch between one and another. So there are several examples in here. For example, the exactly same scenario we have seen. We just put it at night, and we are just tweaking the coloring here and there. Very cheap, and it looks really well. On all the lights and everything that appear, there are just additional objects that we put on top, and with additive blending, we get this illusion of having real-time lights. And here, for example, sandstorm comes, and everything gets very foggy, and just with that. And then we can fade in and out the effects. OK. Now, vertex animated textures is a technique for animating things in the vertex shader in a very performant way. There was the need of there is one armin, which are the Necrons, which when they die, instead of just exploding, they put in the floor some remnants, so they shatter in pieces, and they fall to the ground. So we have 16 cards in play, and we can shatter the 16 cards in play at the same time. Shattering something, you end up with a lot of small objects in the scene doing physics animations. So it was not possible to run that correctly on all devices. So we have to come with an idea for fixing that. And that's where vertex animated texture comes to help. How this works. The end result is, this is the Necron that shatters in pieces. And then you can revive it with another. So the effect looks good, and there is quite a lot of detail in that animation. And imagine that in 16 cards at the same time. So how we do it? The process itself is a bit complex to get it right, but we get the card. Then we shatter it out in pieces. You can use Houdini. We use Blender for that case, but you can use whatever program to shatter that into pieces. And then we get all those pieces and bake the vertex color is telling what's a part. No? So this is a part, and it has like the same color. This is another part, and it has the same color. This is going to be needed in the shader for determining which part you have to move. No? And then we run in the editor a simulation with physics directly, just in the editor. And we bake the result of that simulation into some textures. We bake the rotation into one texture. You need a quaternion, so you need 4 components for doing that, so RGBA for that. And then we bake the position into another texture. That means that in the X position, we have the number of pieces. In this case, is 75 pieces, so it's a kind of complex simulation for mobile. And then in the y-axis, we have the number of frames. In this case, because animation is short and playing it at 15 frames per second was good enough, and we save a lot of memory. You cannot compress this texture, because whatever compression you put in place, it will absolutely break everything. So we got those textures, and we sample that in the vertex shader. And you will say, why one is 150 and the other is 75? Well, the problem with this system is that it's very easy to do mistakes with that, no, in the sampling. So we end up having like a lot of movement in the position. So we have like to increase the size of the texture, even if it's exactly the same, to allow the sampling to work better. And then we just sample that into the shader. Let's check how this works. OK. So we go to Unity. This is how the effect works in this case. OK. And this has several components in place. It has like the main model that we start animating with this crack effect. Whenever it's full, we change that model for the one who has the break inside there, no? Which is the one that is going to move the pieces. And we also change the model which has the pieces. We do that instead of using the same model that has the pieces, because this method has some errors when sampling, and if you always use that shader, you always see the object like broken apart, a little broken apart. So the precision here is important. So we use the main model for that, and in the moment that it happens, we hide it with a little bit of particles, and we change the model and animate it back. No, so. Here is the other model. This is without doing that trick of having the original model and then the other. You say this is just sampling like the first frame of the best animated texture. So you see that you can see a little bit of the cracking, and it's very hard, or you need quite a lot more texture size to try to solve that issue. No? You need more precision in there. You need more memory for fixing that. So instead of that, we get to the solution of toggling one on and off. So in here, the vertical parts start appearing, and whenever it's full, then we start animating the other. Which in here, the only thing that we do is start sampling those textures that we have seen before from top to bottom, and you start seeing just that. OK, and you end up with that. The process is a bit complex and a bit tedious to have everything right from the beginning, and the shader is kind of complex also. So let's check the shader itself. So if we start with the fragment shader, we see here the vertical part where all the cracks start appearing from the top to bottom, so bottom to top, sorry. And here we sample the crack texture, which has in the red channel just the cracks, and in the green channel some variation, so the cracks doesn't go exactly from top to bottom very uniformly, but some one faster than other, no? Then it's just a matter of adding the color in there. And then we mix the normal shading of the car, which is a complex subgraph that we have prepared, and we use in quite a lot of different shaders. Let's check it out, just for the sake of complexity. So yeah, you know, it's how the card is going to draw, how the image is going to draw, everything is in there. And then we can reuse this in any other shader. And then all the heavy lifting comes here in the vertex shader. In the vertex shader, we have a custom function for doing that. And we don't do nodes in this case, because there are quite a lot of mathematical operations to do that, and it's way more convenient in this case to just use some code in there than trying to mimic everything with nodes. OK. Let's go back to the presentation. So wrapping up this, we simulate that, and with that simulation, we get the texture for rotation, the texture for position, and for knowing which part has to read in which part, we use the vertex color. So you have to bake the vertex color, bake the position, bake the rotation. There are some tools like Houdini that has this thing embedded. So they have the shader, they have the toolset directly in engine in the program, and then you can just go and use it directly. Because we wanted to use Blender, we have to do these things manually. This technique has its limitations, and like you cannot do movements that go too far from the object that you are animating because you don't have enough precision to move. No? So it kind of works in the bounding box of the object that you are doing. But you can also use this technique not only for things like shattering in pieces, but also for cloth simulation or fluid simulations or things like that. So it's a very powerful technique that is not very spread, and that you can use for doing animations very performant. There are also even options to animate characters with that. You just have to bake the position of all the bones on everything into a texture, and you do it very fast. There is another issue that you may find, and it's because the operation that you are doing in the shader, in some devices, you may find some issues when sampling that. We run into that issue after launching the game. I don't know if if the players have suffered that, but yeah, we have some issues about that. And it's something that you have to know when you are doing more specific or strange stuff, that you may hit some corners or places that they are not as tested as others, no? Like in the driver or something like that. OK. And shader graph versus coding manually. I don't know you guys, but I have lived a situation of a lot of discussions inside the team about what's good to use shader graph, if it doesn't perform well, that we should write all the shaders by code, things like that. No, I have been several times in that position, and it really doesn't have sense, that discussion, no? Because they are just tools for being used for a purpose. So, and we use both, no? As we have seen, when we use doing the shader manually, coding the shader, we use that when there is like a lot of mathematical operation, like with the sampling the textures for the VIT shader. When there is something that is very specific and you know that you are going to have performance issue, it's a shader that is going to fill the screen, that it's complex, that you have to get the most of the device. So yeah, then normally you have to try to do it manually. If you are doing shaders for UI, we're using Unity 2022, which is the Canvas shader is not yet. In 2023, I suppose it's that. I haven't tried it yet, but if you are using older versions, currently it's not available, updated, or you have to do it manually. I mean, you can do some things with shader graph and for UI, but you suffer a little bit with stencils, something like that. Which is the last point is, if you want really specific parts that shader graph hasn't implemented yet, you have to do it manually, like using stencils. So if you want to do custom blend modes. And when we use shader graph, we use shader graph for most of the shaders in the project. We have seen the shader of the card, so it's the basic of the game, and we also use shader graph for the scenario itself. So we use that because it's easier to use. More people can contribute to doing things in the game. You don't need to fight against the syntax of CE or HLSL. If there is a part that it's not really critical, you can just use it. There is not a big deal. And if you are prototyping, for example, there is a very good workflow where someone just do a very good-looking shader, and then he can pass it to a more technical guy to optimize that. So yeah, my recommendation in this case is use it. You can really use it on mobile. There is no issue about that. You have to remember that there is precision values, and that you can use it, and you can just go to the shader graph and configure each of the nodes what type of precision is using. And the good thing about that is if you have your editor configured in the platform that you are building, it's going to behave very similar to that. So if you are working on multi-platform and you are doing the shaders in PC only, someone on the team should be changing the editor to Android or iOS, so he can test the shader as soon as we are doing that. No? See, if you are doing very complex mathematical operation, just throw there a node, a custom node, and write the code directly. It doesn't have any sense to keep putting nodes for adding, multiplying, quite a lot of numbers together. There is also a trick that you can try to guess how what's the impact that a performance that a node can have, which is just checking the documentation, because all of the nodes has how they are implemented. So you can go there, and if you don't know that if a node is expensive or not, you can just go to documentation, and if there is quite a lot of things going on, you might realize that maybe you are going to have an issue. It's very easy inside a graph to just throw a couple of nodes in there, and you think because there are a few nodes that is going to be cheap, but maybe those nodes are heavy inside, so just go and check the documentation and you will see. You can also use keywords for changing the quality of the materials. We use it in a couple of shaders to adapt them to the different platforms that we're using. Yeah, try to clean everything up, put comments. It's very easy that you end up with a mess. If there is a complex shader, it's very easy to just start throwing nodes in there, but just take your time for tidying everything up and putting comments, so in case that someone else come after you, you know what's happening there. Okay. Thank you, guys.